everyone. Good morning. Thank you for joining us for this presentation. As part of the Wired Wednesday presentation, we are honored to welcome Dr. Roland Stull. Dr. Roland Stull is the chair of Atmospheric Science program at the University of British Columbia. And Dr. Stull's presentation title is Generation Interplay Between Wind, Solar, and Hydropower During Cyclone Passage. Thank you very much, Dr. Stull. And we will open the session for the questions and comments after your presentation. Please go ahead.
Okay, thank you, Fatima, and welcome everyone. I'm delighted to give this presentation. Just a quick background on me. I have a bachelor's degree in engineering, chemical engineering, and my PhD is in atmospheric sciences. And so this is an opportunity for me to help all the engineers on this project anticipate how generation changes between all the different sources of power during a cyclone passage. And also this brings to mind that so far in this project, we've been focusing mostly on solar power. But again, the Wired project is much broader than just solar power and includes wind and hydro and others, also includes transmission lines. And so I'd like to try to bring everything together and sort of anticipating the future of where the Wired consortium here will go in our future research. A lot of what I'll be showing is contributed by my colleague, Dr. Doug McCullough, who was the chief meteorologist at BC Hydro, the primary electric provider in British Columbia. So I'll be talking about what is a mid-latitude cyclone, otherwise known as a low pressure center. We'll talk about typical locations of wind, rain, and clouds, since those are important for renewable energy generation. And then we'll talk about how the variations of that weather does affect wind, hydro, and solar energy production. And then we'll look at other aspects of grid resiliency during cyclone passage. So to start off, what is a cyclone? Well, generically, a cyclone is a synoptic scale, namely thousands of kilometers in diameter, region of relatively low pressure on a weather map. So in this example, showing the Atlantic Ocean, we have a strong cyclone here in eastern Canada with these lines are isobars connecting points of equal pressure. And then we have a high pressure or anticyclone further east in the Atlantic here. And it turns out that the spacing between isobars is a measure of the strength of the pressure gradient. And that's important because the pressure gradient is what drives the winds, which is source of wind power, of course. High pressure, larger spacing between the isobars, weaker pressure gradient, weak winds, often clear skies because the air is subsiding, which is good for solar energy, what we've been focusing on so far. So in general, if we look at a plot of pressure across one line on the weather map, such as the line that was plotted here in the dotted line here, generally high pressure can have low pressure can have very steep pressure gradients near the low, which means strong winds. Whereas high pressure, it's physically impossible to have strong pressure gradients. It's just dynamically not possible. And that's one of the reasons why you get calm, good sunny conditions, and sadly air pollution, air stagnation there. So yeah, so that sort of relates to winds for wind power and sunshine for solar power. So around a low pressure center on a weather map, winds typically rotate counterclockwise in the northern hemisphere. Higher in the troposphere, like if you're 2 or more kilometers above the ground, the winds actually blow parallel to the isobars. The isobars are shown in green here. But right near the ground, in the atmospheric boundary layer, this is like within the bottom a kilometer or so of the atmosphere, turbulence caused by friction against the ground and thermals of warm air rising, the turbulence causes the air to feel drag. And that drag slows the air down a little bit and causes it to cross the isobars at a slight angle towards low pressure. Nonetheless, the winds are spiraling counterclockwise and spiraling in towards the low center. Well, when you hear the word cyclone, many people think of hurricanes, but hurricanes are just one type of cyclone. It's a tropical cyclone. Same with typhoons. They're all names for the same thing, tropical cyclones. However, extratropical cyclones, that's what's affecting our power systems here in North America. Extratropical, they're also known as lows or mid-latitude cyclones. And that's the theme for today is mid-latitude cyclones. One characteristic of mid-latitude cyclones is although they're large synoptic scale systems of weather, um, the bad weather is not um, uniformly associated with the low. Instead, the bad weather is focused in narrow bands, which, as many of you know, are called fronts. So this is an idealized scenario of a low pressure center. The L is written here. We have the isobars shown in black now. So 98 kilopascals, 100 kilopascals, 102 as you get further away from the low. We have a cold front here and often cumuliform, namely thunderstorm clouds right along the cold front. We have the warm front here with a large shield of clouds way ahead of it, and that affects solar power, affects the clouds that affect solar power. We have wind shifts. We have the wind in this sector of the cyclone, known as the warm air sector. Winds are generally coming from the south in the northern hemisphere. In this sector, winds are from the east, and then they spiral around to be from the north and northwest. And often this whole low system is moving across the country towards the northeast. They're moving towards the east and towards poleward. Now, the fronts are often rotating around the low center like spokes of a wheel while this weather is happening. So we'll try to put everything together to see what that means in terms of the interplay and the generation of different types of power systems. So cold fronts again have narrow bands of convective clouds or thunderstorms, heavy, spotty, short-lived rain showers. These are typical views of a thunderstorm with the anvil cloud, and this is the backside of a line of thunderstorms along a very intense cold front. Whereas warm fronts have widespread regions of layered clouds with light drizzle, light rain, well ahead of the front. So way ahead of the front are the very high level ice crystal clouds, the cirrus clouds, closer to the warm front, altostratus clouds. So there's still a lot of light coming in for solar panels here, but it's often more diffuse light. And then the lower clouds, as the warm front gets closer, thicker clouds, less sunlight reaching your solar panels. So let's look at how fronts evolve focused on following the low pressure center. So to set the stage, and again, I have to apologize in advance. Meteorologists like to draw weather maps with a zillion lines on the map. So we'll talk you through this. So here's the low pressure center. We don't have the isobars drawn. So just remember, this is where the pressure is the lowest. We have the cold front here in this example. This is what would appear on a weather map. But in real life, there's not usually a step discontinuity in the weather across the cold front. Instead, there is a frontal zone between the gray band here and the black band here. And the frontal zone is where we have rapid changes in temperature across a short distance. So these red dashed lines are temperature, just a typical scenario. Warm temperatures ahead of the cold front, example 24 degrees, 22 degrees, 20 degrees. But then in the frontal zone, there's a rapid change of temperature across a short distance, 18, 16, 14 degrees Celsius. And then we get into the cooler air behind the front. So in fact, fronts are literally defined as a region of strong temperature change across a short horizontal distance. And these are also known as baroclinic zones in meteorology terminology, where we have strong horizontal gradients, temperature gradients. Now notice in this frontal zone, any one isotherm, so these lines of connecting points of equal temperature are called isotherms. This isotherm is in the frontal zone for a portion, but out of the frontal zone in other portion. So the frontal zone is not associated with any one particular isotherm. It's just associated with a region where isotherms are packed closer together. So it's one of the tricky things to think about. So I'm going to animate now. We're going to fade out the isotherms and look at the pressure associated with this low pressure center. And I should mention this, the whole front is moving towards the southeast here. So let's fade out the temperature. and sticking the isobars. So I left the temperature sort of in light red in the background. So again, we have the lowest pressure at the low center here. Here's 99 kilopascals, 99.5, 100. So further away from the low center, the pressure is rising. But there is one characteristic, and that is along the frontal zone is a relative minimum in pressure. In other words, if you were driving from this location in the southeast, driving towards the northwest, if you drove towards the northwest, you'd start off with a pressure of 100, then the pressure would be 99.5. It would be relative minimum at the front, and then the pressure would increase again as you leave the front. How many of you have barometers at home hanging on your walls? Raise your hand. Oh, shame on you. Shame. Okay, so this is why something like a barometer is useful. Um, a local, as the front approaches, the pressure drops. And so your barometer says bad weather is approaching. And as the front is departing, pressure rises and fair weather is coming in. So that's something to keep in mind there. Okay. Also, we see the isobars often have somewhat sharper kink or bend in them right along the frontal zone. Something else to look for. Okay, let's look at the next feature of weather associated with this front. We'll look at the winds. Well, as we said before, winds in the northern hemisphere tend to go counterclockwise around the low, but in the bottom 1 or 2 kilometers, due to turbulent drag near the ground, the winds are crossing the isobars at a slight angle towards the lower pressure. So what that means is, in this part of the cyclone, ahead of the cold front, namely in the warm air is actually sliding away from the cold front. Whereas behind the cold front, the colder air is advancing and pushing against the cold front. So this wind shift is consistent with cold air advancing, which is the definition of a cold front. The weather associated with this, well, typically scattered thunderstorms, convective showers, more or less right along the front. There may or may not be an additional squall line of thunderstorms ahead of the front. Generally, ahead of the front, the air is warm and hazy, whereas behind the front, you get clearer skies. And then further behind the front, there's scattered cumulus or stratocumulus clouds. So although the front itself is moving to the southeast in this example, the clouds in the front are often moving towards the northeast. Okay, and so there's a wind shift because of how the wind is changing between air at the boundary layer and air higher up. Okay, so what I'm going to show now is an example of a movie loop that just happened just a couple weeks ago. So to set the stage, it might be hard to see. This is Washington State right here. Here's Idaho. Here's Oregon. So Vancouver and UBC is right here. Pacific Ocean is out here. So this is a weak cold front shown by this band of clouds here. And I'll run this animation. And what you need to look for is as the front itself is moving towards the east, approaching, making landfall against the continent, the clouds along the front are moving towards the northeast, whereas the clouds behind the front are moving from the northwest. So let's take a look at this animation. So you get the idea. We have the front is moving to the east, but the clouds along the front are moving towards the northeast, whereas behind the front, the winds are moving from the west. So again, wind and wind shifts are important for wind turbines. The clouds associated with fronts are important for solar power. And of course, along the fronts, there might be precipitation, which helps feed the reservoirs or run of river power systems. So let's move on now to warm fronts, since often cyclones have both warm fronts and cold fronts. So the low pressure center is right here where the L is. Here is the warm front coming out from the low like a spoke of a wheel. The warm front is advancing towards the northeast. Cooler air is moving away. Warmer air is advancing. Again, in this example, the red lines are the isotherms connecting points of equal temperature. And as before, the frontal zone is marked by a region where the isotherms are packed close together, where you have the most rapid change in temperature across a short distance. On weather maps, both warm fronts and cold fronts are indicated on the warm side of the frontal zone. Just the way the standard is. Warm fronts are indicated by the semicircles pointing in the direction that the front is moving. We saw for cold fronts, they were indicated by triangles moving in the direction they're moving. So this is the frontal movement in that direction. So let's superimpose now the isobars associated with this front. Again, the lowest pressure is here. These are lines of equal pressure. So as you get further away from the low, we have higher and higher pressure. Again, relatively low pressure along the front. For warm fronts, the kink in the isobars is not often as strong as they are along cold fronts. But the weather, now I'm going to get to the winds first. So the winds, again, they're going counterclockwise around the low, crossing the isobars at a slight angle. So in this case, we see it's the cooler air that's moving away from the front, and the warmer air is advancing. And so, but believe it or not, a warm front is not defined as a place where warm air is advancing. A warm front is defined as a place where cold air is retreating. And you say, that's weird. Why is that? Well, the reason is warmer air is less dense than cold air. So just because it's advancing, it rises up over top of the cooler air. And so the front itself may not advance even though the warm air is advancing. So that's why a warm front is where the cold air is actually retreating. Pretty weird, eh? Okay. But as that warm air rises up over the cooler air, the warmer air itself cools, water vapor condenses, and you get these clouds way ahead of the surface warm front. So literally many hundreds to thousands of kilometers ahead of the front, we get the cirrus clouds, which is now starting to reduce the solar radiation reaching solar panels. Then the alto mid-level clouds, a little bit thicker, a little more diffuse radiation. Then the lower level clouds closer to the front, which are really reducing the radiation coming in. And then we have the rain bands, thick clouds, and oftentimes, but not always, fog right near the warm frontal passage before the air clears up a bit and becomes warm and hazy. Okay, so um, we've seen in the previous sets of slides how fronts um, change, how we've seen the conditions along a front, along a cold front and a warm front. However, the front itself is evolving as the low pressure evolves. Okay, so let's take it to the next stage of understanding here. So in this view, we're looking at a map, again, north, east, south, and west. We have a region of clouds shown by the gray shading. Again, as meteorologists like to put too many lines on the same map, the dashed red lines are the isotherms. Again, the packing of isotherms indicates a frontal zone here. And then we have the isobars shown in black, pressure. So here we're starting with a stationary front, indicated with the warm and cold symbols on opposite sides of the front. This front's not moving very much. The pressure's not very low along it, but it still exists. And so nothing exciting is happening. But sometimes higher in the troposphere, 30, 40,000 feet for you Americans, or on the order of 11 and 12 kilometers for scientists and engineers and Canadians, there'll be the jet stream will actually start to suck air molecules away from a particular region over the Earth's surface. And as the jet stream sucks out air molecules, it leaves lower pressure at the surface. And so now we have the birth of a low, namely cyclogenesis. So the pressure started to drop, and now we have a pressure gradient, which is causing winds to circulate around them, which causes the warm air to start advancing as a very weak warm front, and cold air back behind it to advance as a cold front. But if that upper air support in the jet stream continues to suck out air molecules from the column of air here, then the surface pressure will continue to deepen. The low gets stronger, the pressure gets lower. We have now closer spacing between isobars, which cause stronger winds around it. The cold front is advancing, the warm front is advancing. We're starting to get the cloud shield way ahead of the warm front of the layered clouds. And then the narrow band of thunderstorms. Again, the gray shading indicates the clouds here. if the support continues, the upper air support, then the low continues to strengthen to a very intense low, very strong winds, important for wind turbines. Namely, they could generate lots of power unless the winds are too strong, and then we have the cutout of the wind turbines. So this is often the strongest stage of a mid-latitude cyclone, lowest pressure in the center. The cold front, though, is often moving faster than the warm front. And the cold front can catch up to the warm front and make what's called an occluded front here, where the different warm and cold frontal symbols are on the same side of the front. So this is a front that has characteristics both of a cold front and a warm front all happening at the same time, at the portion where the cold front caught up to the warm front. So this is called the occluding stage of the cyclone. It's starting to die now. The pressure is not as low in the low center. The winds are starting to wind down, become weaker. And as this continues, we end up with this very classic spiral band of clouds shown in gray, with often clearer air being drawn into the cyclone. This is an occluded stage of the cyclone. It's dying. The pressure is rising. It's not a stronger pressure gradient. Winds are weaker. And um, and these are very classic pictures. You see these in satellite pictures. Talk about a cinnamon bun looking picture here. This is near Iceland here, an occluding low pressure center where the spiral cloud bands are wrapped around and around many times. So just by looking at the map, you can figure out what stage the cyclone is in. And eventually the cyclone literally winds down. They're just scattered clouds, just weakly spinning around. And we're sort of left with the stationary front back where the action is, and a low pressure can form again. So that's a typical evolution life cycle of a cyclone, mid-latitude cyclone and its fronts. However, while that's happening, the whole cyclone is moving. Okay, so this shows here's North America here, the Atlantic Ocean, Pacific Ocean, and it shows typical tracks of mid-latitude cyclones. In this case, this is for January. This is wintertime cyclones. And so, in other words, we need to consider how the cyclone is evolving while the cyclone is moving, moving over wind farms, moving over solar panels, moving over hydro reservoirs. Um, so this sort of tries to put everything together. Again, we're looking down on a weather map, and this shows the cyclogenesis. A low is just forming here, and what used to be a stationary front. As the low strengthens, the low is moving to this location shown in gray. The cold front is advancing, the warm front is advancing. As time continues, the low continues moving to the northeast. The cold front continues to advance. The warm front is advancing. The low is strengthening. This is the strongest point here. But then the life cycle of the whole lull is only like 2 or 3 days. So it's already starting to die now in the occluded stage, shown in green here. And as the low moves up here, we've reached the very occluded stage, the dying stage. And then, so we see the cyclone is moving while the fronts are revolving. So all this is happening all at the same time. So be thankful that you have numerical weather prediction models that predict, what's going to happen, where are the clouds, where's the rain, where's the sun, how's it going to change. And of course, these days, artificial intelligence is starting to take over in the numerical weather prediction business. So I took this from an article. It looks scary, it looks complicated. Here's a low pressure center with the front, the stratiform clouds ahead of the warm front, clearer air behind the cold front, thunderstorms along the cold front. And for those of you along the West Coast, in California, Oregon, Washington, and Vancouver, often ahead of the cold front is a prefrontal jet, also known as the atmospheric river, which causes flooding, which is another issue for hydroelectric companies. So, being that I'm a teacher, this is a test for you. If you saw clouds in a satellite picture, would you be able to identify where the fronts are in this? Okay, just think about it. Okay. Um, so hopefully you'd see the cold front would be there, the warm front would be there, and the occluded front would be there. Okay, so just by looking at this, it looks like a walking cane or something, a little spiral band. We know that's already occluded. How about this one? Okay, well, again, putting on your thinking cap, you probably guess the cold front is here, the warm front is here. and the occluded front is there. So the storm is already occluding. Okay. Well, this is a numerical weather prediction model. This is not a satellite picture. And if I were to run this as an animation, which I didn't save, you'd see the winds going counterclockwise. So you'd identify this is probably a low center. And this looks like a cold front. Winds are coming off of Nova Scotia and Newfoundland, Labrador, and then a sudden wind shift along the cold front here. So I would say the cold front is here where the wind shift is. Winds are from the south, southwest ahead of the front, from the northwest behind the front. There's another wind shift right here. So it looks like the cooler air is sliding away from the front, the warmer air is advancing. This is the warm front. And then, of course, we have the wind changes around the occluded front and the low pressure center. So you get the idea. See these pictures? Again, here's Washington, Oregon, here's Utah. Okay, so we see us already the warm frontal clouds are hitting Utah, even though the cold front's back here and the occluded front is wrapping around the low that hasn't even made landfall against Vancouver Island yet. Okay, and another cyclone bomb. This is from last year. Just a cyclone bomb is by definition where the low pressure center drops so fast it deepens 24 millibars, 24 hectopascals in 24 hours. And this happened to be a cyclone bomb that made landfall, had strong winds. Okay, so let's get back to power now. This is the variations of wind, hydro, and solar power during cyclone passage. So we'll start off with a very idealized, simplified scenario, and then later on think about how this applies to real life wired grid networks where there's solar panels and wind power turbines and hydro reservoirs all over a large area. But for now, let's look at an idealized situation where in a small region, let's suppose you just have neighborhood wind power, solar panels on the roof of your university or research institute, and maybe a small neighborhood run-of-river power station here, all in one physical location. Okay, so, and let's suppose that there's this low pressure center that's approaching this region where you have wind, solar, and hydropower all together. Okay, so I'm going to run this animation. The low pressures are approaching your power center here. We get the clouds affecting the solar power, wind increases. You get some rain, you get some wind, you get thunderstorms, the wind change, and then it gets clear again, right? So this is what's happening at this one local power center. So we can reframe this and say, okay, relative to the low center itself, this is where the power center was at noon on day 0. By midnight on day 1, your power center was at this location relative to the low, noon, day 1, midnight, day 2, noon, and so forth. So we can ask ourselves, what kind of weather and what kind of power generation is happening as the cyclone is passing over your power center, namely relative to each of these locations relative to the cyclone. We're assuming the whole cyclone is moving, it's translating at 40 kilometers per hour to the northeast. Well, so in this first stage here, okay, we can look at the weather. This is from noon to midnight on day 1, or midnight to noon. So the pressure is falling as the front approaches and then rises after the warm front passes. The wind is from the east ahead of the warm front, increasing in speed, so there's more hydropower generation. Then the wind shifts to the southeast after the warm front passes. The temperature, well, why do we care about temperature? Because that's important for electric load and the demand on the ampacity of the transmission lines, right? More people turning on their air conditioners or whatever. So temperature is modest in this particular time and then rises as the warm front approaches and then rises sharply as the warm front passes. The sky condition is overcast, widespread overcast with nimbostratus and rain showers, light rain moving in at 4 a.m. and then moving off after 10 a.m. And rain, light rain and drizzle, occasionally moderate rain, ending as the warm front passes. So that's initially. And then your power center is in this warm air sector next, and this region circled here. From day 1 noon to the next midnight, pressure rises slightly, but then holds steady. The wind eases to the southerly 10 kilometers per hour. The wind is your power center is in the warm air sector now of the cyclone. The temperature's warm, the air conditioners are turned up, sky condition, humid conditions, scattered clouds, stratocumulus clouds, maybe increasing as the cold front approaches, but it's not raining. It's dry. So no input to any hydro reservoirs. But since we were considering run of river, that means, maybe not much river run power generation yet. But then as we get to midnight to 12 noon on day two, now we're getting the cold front passes. The pressure falls as the front approaches, reaching a minimum around noon when the cold front passes. The winds are picking up to 20 to 30 kilometers per hour, maybe gusting to 65 as the cold front passes. Temperature initially warm in the warm air sector, but when the cold front passes, the temperature drops rapidly back down to 12 degrees. Sky is overcast, uh, scattered showers, towering cumulus clouds. One of the weird things about towering cumulus clouds is while they provide shadow over your solar panels, if you have a towering cloud off to the side of the solar panel, you can not only get sunlight directly in the solar panel, you get reflection of sunlight off the high clouds that allows you to have greater solar generation than you expect in normal clear sky conditions. Interesting. And then rain, dry through the morning, but then the heavy showers when the storm passes. And then finally, you're behind the front. The pressure rises as the front moves away. The winds are gradually, they remain from the west to northwest, pretty strong with gusts of 50 kilometers per hour, and then easing to 10 to 15 kilometers per hour. The temperature initially was dropping, but gradually rises in the sunnier conditions behind the cold front. The convective clouds move away. There might be scattered clouds in the afternoon, and moderate rain showers through the afternoon have been clearing in the evening. So that gives you an idea of the typical evolution of weather. So what about electric generation? Okay, well, during day one, circled in blue, looking at your small run-of-river hydro plant, runoff through the rain increases through the morning and eases in the rest of the day. Your power production follows the hydrograph curve, the runoff of your stream flow. Your wind farm, power increased in the morning and eases by late morning into afternoon, um, with light power production the rest of the evening when you're in the warm air sector. In the solar generation, little production in the morning due to this widespread shield of stratiform clouds. But then once the warm front passes, you're in a clearer air, moderate production in the afternoon. The air could still be pretty hazy then. But then in day two, power hydropower increased, particularly when you have the heavy rain showers, and then the power drops off as the stream flow drains itself out. Wind farm, very strong increase in wind power production. In this particular example, not strong enough to cause the wind power to cut off. But again, for stronger storms, that is a concern. And then moderate production after the cold front passes behind that. So that was an idealized scenario. Now let's look at real weather, but again, for an idealized power center that had hydro, wind, and solar power all at the same location as you have a cyclone passes. So this is using weather data from the UBC weather station in Vancouver and making use of streamflow data from the stream just north of University of British Columbia. So what we're looking at now is pressure plotted versus, trying to move this so you can see it better. Pressure plotted versus time over a 7-day period. So this is actual frontal passage. Pressure dropped as a cool front approached. FROPA is the nickname for frontal passage. Then the pressure rose. Then the next front came, the pressure dropped. The pressure rose. Next front came. And then we have this anticyclone of fair weather and sunny skies. So we see temperature was rising ahead. And then we had cold frontal passage, temperature decreased. Then we had warm frontal passage, temperature increased. And then we had cold front that left cold air, anticyclone. So what about precipitation? Well, this shows the precipitation rate every hour. And we have precipitation preceding the frontal passages. The frontal passages are shown by the red lines. Precipitation accumulating during the course of the storm in millimeters here, and the stream flow in cubic millimeters per second. Typical hydrograph reaching a peak near the end of the rain, and then a gentle recession after that, the next peak from the next rainstorm, and then recession. And this last frontal passage didn't have much of a peak. So again, these are actual stream flows. Well, again, for these three frontal passages, what about wind speed for wind power generation? Well, the wind picked up before the first front, and then a wind change in direction, and another peak in wind right after frontal passage. This next front didn't have much of an increase in wind speed, and the third front, again, not much. And then in the high pressure, nearly calm conditions, nothing exciting, not much generation of power. And then, of course, these wind direction changes. So what about humidity and radiation for solar panels? Well, again, here we have the pressure trace showing the three fronts, humidity trace, but more importantly here, look at the solar radiation. A lot of clouds, not much sunlight coming in, a bit more sunlight coming in during the day before the third front passed. But after that last front passed and the cold air entered the system, clear skies, lots of solar power produced during the daytime, nothing produced at night. Um, this was a November situation, so the days are short. This is Canada after all. All right. Okay. So what is the power generation? Okay. So combining all those power indicators, the run-of-river hydropower, peak production, in the first frontal passage and afterwards some hydro production there. So we're looking at megawatts of production shown by the solid line, and then looking at the total energy produced in megawatt hours that's shown by the dotted line here by the end of this 7-day period. Looking at wind power, again, a lot of production in megawatts shown by the solid line, not much after that. And so for this particular small wind turbine, this is the total energy in megawatt hours at the end of the 7 days. Solar power, not much to begin with, a little bit more before the third front passes, but then in the clear air after the third front passes, a lot of megawatts from this little solar power station and the accumulated energy shown by the dotted line. So combining them all together, we have the hydropower shown in blue, this curve here. We have the wind power shown in purple, and we have the solar power shown in red, and the total, the sum of them all, shown here. So again, as these different cyclones and fronts passed, quite a variety of interaction of which power production method was dominant. And then again, looking at the total energy produced in megawatt hours as over the 7-day period. The sum here, initial contributions from hydropower, but then also from wind power and solar power at the end, contributing to the total power production, total energy production. Okay, so since in different parts of cyclone passage there might be clouds, so not much solar production, but there might be more wind. So that's why more and more companies are combining multiple power systems. So this is an example of wind and solar, so that when the clouds come over, hopefully the winds are picking up, you're still generating power. And here's an example of solar and hydro from a hydroelectric dam. They installed solar panels on it. Um, and there's also solar and no, there's also wind and hydro. I don't have a picture of it that have been combined. Okay, so what are some of the aspects of weather here on grid resiliency? I mean, heck, the whole name of the project is grid resiliency, right? So it's not just generation, it's electric load, it's the demand for electricity, it's the capacity of the transmission lines, it's your reservoir capacity versus mandated stream flows downstream of the dams. There's issues, particularly in Canada, with floods and ice jams. What about high wind issues, blowing trees down on power lines, or winds so strong that the turbines cut out, or public safety power shutoffs to prevent wildfires? And then, of course, wildfire, wind, and smoke, which I won't talk about because we spent a lot of time talking about that already in my previous talk. So let's look at electric load. As many of you know, typical electric load each day is double peak. There's a peak in morning, rush hour, people eating breakfast, turning on their toasters. and then a bigger peak in the evening, supper time, turning on the TV, and then decrease at night. And of course, this is varying. Um, it varies weekly. It's different on weekends and weekdays. And so, for example, this is a study we did where we just looked at the second peak in each day, and we looked at the climate trends of this afternoon peak, load in megawatt hours for BC Hydro. And of course, there's might be climate change happening over the years from 2004 to 2008. So these are annual cycles here with a climate trend. So we can remove the climate trend to just get the annual cycle. And then we can remove the annual cycle, fitting that, and gets what's left. It was interesting that what we see is a semi-annual cycle, shown in red here, with a lot of variation. The blue line shows the rest of the variation, and that's my business to help you predict the electric load that's needed, right? So this is due to weather variations, mostly a little bit due to psychology, which I'll talk about. So the load, how much electricity people use depends quite a bit on temperature for home heating and air conditioning, depends on cloudiness, obviously, depends on wind, depends on precipitation and humidity, and believe it or not, depends on psychology. BC Hydro had one case where snow was in the forecast. All the homeowners cranked up their thermostats, but then the snow never came. But there still was a big load because of the humans turning on their heat in anticipation of the snow. So this is a tough one to predict. And then there's various load forecast methods to predict electric load based on weather forecast input. Neural networks have been used for decades. Um, Genetic programming, my team did some work on this, and of course, artificial intelligence is a big um, method these days for load forecasting. Well, what about another issue? Ampacity. How much electricity can your power lines carry? When you have this big load at one end, you have your power production at a different end, you got to get the power to the users. And I think in the States, you guys are lucky. You have power lines crisscrossing the country all over the place. But in British Columbia, we have a lot of power production in north central BC, and when there's one big power line coming down through the center of the country to bring all the power to Vancouver and then to sell it into Seattle and to California and so forth. So, but there's an IEEE standard that tells us how to calculate the maximum current, the ampacity, that a conductor can carry in conditions of use without exceeding the temperature rating of the conductor, right? If you put too much electricity through your conductor to your transmission line, it gets too hot, which can cause annealing of the metal, which changes its not only mechanical properties, but also its electrical properties. And another issue is sag. As the lines expand, as they get hot, they can get closer to the ground, touch trees, and ignite wildfires. And so this IEEE standard, has inputs of temperature, wind speed, and direction, pressure, precipitation, and sunshine. And a lot of these, like the wind and the sunshine, depend on the angle, different parts of the transmission line. And so my team came up with a simplified three-segment way to approximate a catenary shape to make it easier to calculate all these angles of sunlight that's heating the line and wind direction relative to the line and so forth. So Maggie Campbell did her master's thesis on that quite a few years ago. And in fact, this shows some of her work. This shows, here's Vancouver down here to set the stage. And this is one of the transmission lines in BC Hydro's system. And so what we can do is we can take the weather forecast at each point along this line, calculate its ampacity. The ampacity is now color-coded here, where red is lower amperage is allowed because the line's already so hot, the winds are light, and blue means it's better line. Now, as you know, um, for current, since a lot of you are electrical engineers and stuff, um, the weak point, the weak link in the line controls the current through the whole line. Okay, assuming there's no other inputs or output along the line. So wherever you have the one worst ampacity, that affects the transmission of the whole line here. So I'm going to run this animation here. You'll be able to see as the day progresses. This is at 1 in the morning, namely nighttime Pacific time. It's a large amount of current can be carried, but by 6 in the morning, already there's the ampacity has worsened. It's shown in reds here. It's even worse. And by the way, the worst point of ampacity is always highlighted, and it changes to different points on the line. It's not always the same point. Okay, and then here the worst ampacity is down here. This is at 6 p.m. local time, and then by an hour before midnight, the ampacity is really bad along the whole line here. So again, by doing these ampacity forecasts based on the weather, we can help utility companies figure out, where are the places that are frequently causing the weakest link, and those maybe they can enhance the transmission line there to not make it a weak link. Well, there's other issues related to weather. Regarding hydroelectricity, various treaties and government policies mandate a certain stream flow downwind of the hydro dam, such as recreation in the lake of the reservoir, or stream flow for fisheries, or flood control, or dust control. If you lower the reservoir too much, then you have exposed sediment. When the wind picks up, it causes dust storm that affects indigenous communities. But of course, hydroelectric plants prefer to maximize their water level to get the best pressure head and max electric generation. But they want to avoid dam failure and overtopping the dam. So if there's a heavy rain in the forecast in their watershed, they need to lower their water level to make space to hold the new water that's going to come in. But they don't want to lower the water level because water is revenue. So they really rely on the forecast to try to run as much water through the turbines instead of just releasing it in order to make space for the next storm that's coming in. And of course, flood control is a very important issue for hydroelectricity. The dams would rather not spill water because that's lost revenue. But then again, they have to manage the reservoir level. If you have too much water going downstream of the dam, that can also cause floods downstream. Now, something you may not have to worry about so much in the States, but we have to worry about in Canada, is ice jams on the rivers. Doggone it. This cold weather, here's the Peace River, Alberta and British Columbia. The cold water is flowing down from the north sorry, rephrase that. The Peace River is flowing north towards the Arctic Ocean. I got it wrong. But the cold temperatures are causing freezing, moving south. So you have water moving south, cold air moving north. I got it wrong. Water's moving north, cold air is moving south, and you have this ice front that's moving south. So this actually shows the location of the ice front versus time as the winter progresses. And when the ice front gets near towns, it can jam up the water, but still trying to flow, causing flooding of nearby communities. So that's an important issue for BC Hydro. They need to modify the stream flow to try to reduce the ice jam flooding. And so we had my research team, Lynn Engel on our team, and colleagues were doing some research to look at forecasting ice flooding. What about tree blowdown issues on power lines? Okay, again, another weather-related phenomena. So here's the west coast of North America. You folks in Utah, you're over here. Here's a cyclone that's approaching the west coast of the Pacific Northwest with its cold front, its warm front, and its low. Strong winds, gust, power line faults, customers without power in this particular couple-year period we're looking at here. But my team was forecasting the weather. This was our forecast of wind. I know you can't see each individual arrow here, but the reds and the purples and blacks are fast winds. The blues are slow winds. And this was a time when we actually were successful in forecasting very, very strong winds, causing power line failures all over Vancouver. Trees were blown down in Stanley Park. It was a big deal. Now, also another wind issue is wind turbine cutout. If you look at power production versus wind speed, power increases, the wind speed increases, then you reach the rated power. But if wind is too strong, then to protect the turbine, they feather the blades, they stop the blades from rotating, and you have power cutout. That's important for your utility companies. They need to know when that's going to happen, doggone it. And so here's an example of a high pressure region, not a cyclone, but along the Rocky Mountains here's British Columbia, here's Washington State. the isobars are close together, getting strong winds. And that caused power cutouts, which I'll show in a second. Another issue is that although any one wind turbine might have this power rating curve, the collection of wind turbines at a wind farm does not at all look like that power curve. These are actual power curves from 4 separate wind farms in British Columbia. Now, they've all been normalized to protect the identity of the wind farms, but first of all, this power rise here never follows the cubed power law you get from a theoretical that, power increases with the cube of wind speed. It's never cubed in real life. It's less than that. And then you have this power drop off happening sooner because some turbines in the farm are in fast winds, others are in slower winds. So for that wind farm in the Rocky Mountains, they were getting wind speeds here of 30 meters per second that exceeded their cutout speed of 25 meters per second, shown in purple here. And their power production, of course, was greatly cut down here um, due to the feathering of the wind turbines, high wind issues. So another issue, of course, in high wind is the public safety power shutoffs on hot days when the power lines are sagging, winds are blowing the power lines against the trees and starting fires. And so issues in weather, fast winds, no recent precipitation causing dry vegetation, high temperature and low humidity. And again, this relates not only to high pressure fair weather regions, but fronts and downslope windstorms, particularly in California, like the Santa Ana winds and the Diablo winds that happen when you have high pressure blowing air across the Sierra Nevada mountains. So just to plug, we do teach a course on renewable energy meteorology here at UBC. It's an online course, and you can take it remotely. It just has an in-person final exam that we can arrange for that. It covers hydropower, weather, wind power, weather, solar power, weather. A lot of the slides that I presented today are taken from this course, and the instructor is Dr. Doug McCollar. So we'll bring it to an end here, and we'll have a minute or two for questions because I actually have another Zoom call I need to get to in 5 minutes, which is relating to the forest fires and blue sky smoke. So we'll open it up for questions here.
Yeah, thank you so much for the insightful presentation. And we would like now to open the session for questions and comments. Please go ahead, Dr. Parvania.
Thank you, Roland. This was such a great presentation, very relevant to what we are doing. So my question is actually regarding your plug. So we've been thinking and like to like how there is a lot of like a kind of a like education that we have we are doing across the center, a lot of courses, and the part of like the mission of Wired is to actually train students to know beyond just like, for example, atmospheric science, power grid, data science and stuff, right? So my question is that how can you enable the students to take that course and perhaps get credit for that in their home institution? I would like to work with you offline to see how we can enable that. Perhaps like, I don't know, like offering courses as part of Wired if we can do anything. I think that's very critical. And for example, I teach a course that I'm sure some people can take, like Hamid teaches course, like Mustafa and many other faculty. I thought like John is also in this meeting. John teaches a course in University of Utah that some of my students took. So I think there are a lot of courses that we want to make sure that many students take. So I will follow up on that.
Yeah, we can do that afterwards. Yeah. For those of you in Alberta, there's already a dean's agreement between British Columbia and Alberta regarding sharing of courses and so forth. But many of you are in many other places, particularly in the States, and I'm happy to figure out a way to make it work.
Thank you.
Okay, so one more question. I do need to leave in a minute or two, so go ahead.
Sure. Thanks, Dr. Roland. My question is how much of this cyclone passage is a concern for other provinces such as Alberta or maybe in Yukon or Northwest Territories?
It's concerned at all those places because the cyclones are often moving from, the west to the east across the states, Pacific Northwest, across the Rocky Mountains into Alberta, and also often just east of the Rocky Mountains, both in Canada and in the States, cyclones intensify. It's known as Lee cyclogenesis. So you get cyclones strengthening in Alberta and then causing havoc across the prairie provinces and the plain states of the US. So Again, I have to apologize, but I need to go to the next meeting because I'm actually leading that next meeting. So again, I had fun. Hope you guys had fun, and feel free to email me. My email is there. Yeah, take care, everyone. Bye-bye.
Thank you, everyone. Thank you, everyone.